Well, thank you very much, Jim, and I apologize for the inconvenience. It was a little bit difficult to uh, experience teleportation from Baton Rouge all the way to Singapore in less than
We'll forgive you.
25 hours. But it's a great pleasure to be able to share with you this work that we've been pursuing with Gary and Jimmy Wang, and most recently with Lakshmi and James Durant and Danwei Wang on studies of water oxidation photosystem 2 and as well as on metal oxide surfaces. As you know, our work started about 14 years ago, trying to understand the structure and functionality of the oxygen evolving complex with an interest in learning the underlying mechanism and the structural aspects of the oxygen evolving complex, and then use knowledge to develop materials that are functionalized with biomimetic oxomanganese complexes or other water oxidation complexes that could be bound to metal oxides and then um, be activated with solar light in an analogous way as it happens in the flaccid membrane of green chloroplasts. If that was possible, then we could use water as the ultimate source of electrons and protons, and those be used to produce fuels in the same way as it happens in plants. So, as you all know, our work started with the breakthroughs in X-ray crystallography that came from Jim Barber and coworkers with a structure at 3.5 angstrom resolution, where the model of the oxygen evolving complex based on a colloidal structure of four manganese centers and a calcium was proposed not only on the basis of the overall electron density map that came out of the diffraction data, but also trying to match manganese distances that were consistent with previous studies based on X-ray absorption, and as well as with a model of the colloidal structure inspired by EPR work from David and Brett and coworkers. Now, many of the structural aspects in this model, such as the presence of bicarbonate that was subsequently retracted, had to be completed since the presence of water was not resolved in the diffraction data, and the coordination sphere of each of the manganese centers was partially incomplete. Nevertheless, we thought that this structure, even with the presence of radiation damage and structural disorder, was the best possible empirical model for building a computational structural model that was chemically sensible. So we decided to use this empirical model and define the oxidation state of the manganese centers as revealed by EPR spectroscopy, and then completed by hydration, the presence of chloride, and relaxation of the environment to see whether the structure of the oxygen evolving complex could reveal the true nature of the catalyst in the high valence state. And the methodology that we used was this combination of quantum mechanics, molecular mechanics techniques, where we include not only an extended quantum mechanical layer that included the oxygen evolving complex and all of the ligands, surrounding ligands and cofactors, but also the surrounding protein, so that coordination sphere effects and beyond, including the long-range electrostatic interaction with the surrounding environment, could be explicitly included. And to the standard electronic embedding methodology available in Gaussian, we supplemented a technique that is called self-consistent polarization method that we developed to enable polarization of the cavity as well, self-consistent with the distribution of charge, the oxygen evolving complex, and the surrounding environment. With this technique, the well, this technique finally was awarded the Nobel Prize in 2013 for Martin Karplus, Michael Levitt, and Ari Warshel, who actually posed this combination quantum mechanics kinetics and molecular mechanics methods. And it was useful for a wide range of applications, including studies of photosynthesis in green leaves. Most recently, we had extended the QM layer to a very, very large quantum mechanical layer that includes more than 324 atoms, so that we could address isotope effects, mechanistic analysis of the whole bond formation that could be compared directly to kinetic data. So not only these QMMM techniques allow us to include a very large QM layer, but also the influence surrounding protein of this QM layer. And with that method, we proposed that the model that was most consistent with this relaxation of the cluster in the presence of the surrounding environment was this colloidal structure with an additional mioxo bridge that was not initially proposed by the X-ray diffraction data, and then had terminal molecules bound to dangling manganese and to calcium, and also had complete coordination sphere for each of the manganese centers. We also proposed chloride because it was known that evolution would stop by chloride depletion. And we suggested at the time that these two water molecules could be responsible for the oil bond formation through the nucleophilic attack for the hydroperoxide intermediate, very much along the lines of early proposals by Vincent Pecoraro and Gary Bradvick, who had analyzed oxomanganese complexes and had suggested a similar mechanism. And nevertheless, this colloidal structure with the dangling manganese was initially ruled out by EXAF's studies from the Berkeley group, but subsequently confirmed by X-ray diffraction and by Shen and Cookers in 2011 with a 1.9 angstrom resolution that finally confirmed the presence of the colloidal structure with the dangling manganese, the additional mioxo bridge linking dangling manganese with manganese 3, even the presence of terminal water molecules that were confirmed for the first time with the work of Shen and co-workers. Even chloride was resolved for the first time near the OEC, not exactly where we had suggested it, but after correcting the coordination of aspartate 170 that we had suggested to be monoacetate to the dangling manganese and making a bridge between dangling manganese and calcium, then chloride relocated to the actual position. And with these two models, this QMM model, we could enable the validation of the model, direct comparisons to high-resolution EXAFS data. And we showed that, in fact, the colloidal structure with this dangling manganese produces EXAFS data in very nice agreement with experimental work by Holger Dow and co-workers. On the left, these are comparisons to isotropic EXAFS, as well as to the beautiful data from the Junko Yano and co-workers on polarized EXAFS that enable the collection of the analogous results on single crystals of these two. But with this model now, we could address the structural rearrangements that are induced by activation, and also the spectroscopic changes that reveal those structural changes. One of the aspects that has been observed for a long time is this bimodal distribution in data of the S0 state that coalesces to a single band in the S1 state, simply because the distances become, and the distances between manganese centers become more similar and uniform. What we did was to start with our model of the S0 state and investigate which one of the manganese centers would be more easily oxidized. And from all of the three choices that can in our model, where only manganese 2 in this case is in the oxidation state 4 and all the others are manganese 3, we found that manganese 3 is the one that gets oxidized more easily. And when it becomes a stronger Lewis acid in the S1 state, it coordinates and OH ligand to dangling manganese and forms a dimeoxo structure with a shorter manganese-manganese distance, much more similar to the manganese-manganese distances between metal centers in the colloidal structure. And therefore, this difference of the 2.9 distance associated with manganese 4, manganese 3, and the other distances at 2.7 become all more similar between 2.7 and 2.8 in the S1 state. And this transformation basically suggests that due to the oxidation of manganese 3, the pKa of OH ligand is reduced and gets detonated using a PCT transformation that is revealed by these changes in the XAPS data. So finally, we were able to have models that enable us to explore subsequent changes and make direct comparisons with the most recent advances in serial X-ray crystallography. So one of the experiments that have been reported is analysis of structural rearrangements after 2 flashes of light when the OEC is advanced from S1 to the S3 state. The earlier work that we use for comparisons is data reported by Petra from ASU. And what we did was to analyze the isomorphosphere differences in electronic density between S3 and S1. And from our QMM structures, we could compute there is a depletion of electronic density at the center of the colloidal structure that is very much consistent with the decrease in electronic density revealed by these femtosecond X-ray crystallography data. The reason why the electronic density is reduced at the center of the colloidal structure is because in the S2 to S3 transition, there is a water molecule that binds to the cluster. In our model, it binds to manganese 4, forming an additional muoxo bridge and separating this part of the cluster relative to the rest of the OEC, and therefore reducing the electronic density. And this was in principle initially counterintuitive, because one would assume that when the manganese centers get fully oxidized to the state of oxidation state 4, then the cluster would be more compact. Nevertheless, the binding of an additional water molecule and forming this additional muoxo bridge gives an interpretation of this reduction of the electronic density in the center of the colloidal structure because of this rearrangement of this part of the cluster relative to the other. This supply of water molecule in the S2 to S3 transition to this carousel rearrangement around manganese 4 was supported by direct comparisons with ammonia binding. We use ammonia as a chemical analog of water binding, and we explore where ammonia would bind and produce a structure that was most consistent with XAPS data reported by Holger Dow and co-workers. And from all the possibilities that we investigated, we concluded that the binding site that was probably most consistent with the experiment was binding ammonia as an additional ligand to the dangling manganese, not substituting the water ligand, but rather as an additional ligand to this dangling manganese, suggesting that substrate water molecules might bind analogously. And by adding as an additional ligand, ammonia induces this rearrangement of water ligands around the dangling manganese, suggesting that when water is supplied through this channel, also induces structural rearrangement of the other ligands in carousel around the manganese 4, leading to binding of water to and forming this additional muoxo bridge between and the dangling manganese. So with this hypothesis, we decided to search for experimental data that would confirm or otherwise rule out this binding of substrate water molecule. And we analyzed most recent data, beautiful data by Shen and co-workers of femtosecond X-ray crystallography and 1.9 angstrom resolution. And what we find here is evidence for this carousel mechanism, because there is a depletion of electronic density at the position of what X that would enter the carousel, and there is an increase in electronic density associated with the ligand manganese 1 that is formed upon displacement of oxygen 5 into its new position. So that is exactly what you would expect if the water molecule would enter this carousel, and oxygen 5 would get displaced, forming this new ligand of manganese 1. So another piece of experimental data that seems to be consistent with the mechanism of subgroup binding is the most recent data by Lakshmi and co-workers. These are high resolution EPR data, where she sees that in the presence of ammonia, all of the protons that were already there due to water ligands remain very much the same. But in addition to those protons, there are additional protons due to ammonia binding. Also very much consistent with this suggestion of ammonia binding as an additional link to the manganese. So with this in place, we decided to address the critical question of the oil bond formation, and that basically is the most unclear part of the mechanistic cycle. And so for comparisons with the mechanism, we had to match kinetic data based on time to solve fluorescence, reporting characteristic time for the oil bond formation between 1 and 2 milliseconds. And this is work by Holger and co-workers, where you could monitor the fluorescence of manganese and see that it decreases when a manganese center gets oxidized, simply because the electronic density is reduced, so there are fewer electrons, and the density of X-ray fluorescence decreases upon oxidation. By feeding these decays, characteristic time can be extracted. So from the S1 to S2 state, Holger extracts the characteristic time of 70 picoseconds, from the S2 to S3, 190. And when he flashes the S3 state, rather than seeing another decrease of electron intensity due to formation of the S4 state, what he sees is an increase in the fluorescence, because the OEC doesn't stop at the S4 state, but it forms directly the S0 state on the oil bond formation. And that transformation from the S3 to S0 state is in the mid-second time scale, as revealed by this trace. And of course, this comes right after a lag phase, and that has been ascribed to deprotonation because it's sensitive pH. So this is one of the aspects that the mechanism must fulfill. And another aspect is that oil bond formation is pH independent. So the limiting step in the mechanism cannot be deprotonation of the OEC, but rather oil formation. If there is deprotonation, it has to come after oil bond formation, simply because that step is pH independent. This might become in the discussion session. But another piece of experimental data that has to be consistent with whatever mechanism is proposed for the oil bond formation is the most recent work by Bradley and co-workers, who was, for the first time, Gary was able to measure a kinetic isotope effect. And for a long time, people tried to investigate whether the oil bond formation distilled oxygen 18 relative to oxygen 16, simply because in the atmosphere they reached the composition of oxygen when compared to the corresponding isotopic composition of water in the ocean. And nobody was successful at observing that, simply because in the rate limiting step in photosynthesis is the exchange of the quinone by the plastoquinol by plastoquinone, and because the acceptor side is rate limiting. So what Gary did was to increase the concentration of quinone, which is usually 8 to 1, 400 to 1 and beyond. And when that concentration is that high, then the acceptor site is no longer rate limiting, and there is evidence for a kinetic isotope effect due to bond formation. And the kinetic isotope effect that Gary reports is 22 per thousand with this small experimental error. And so again, if a mechanism is consistent with experiment, it would have to have an analogous kinetic isotope effect. In addition, Gary also measured deuterium isotope effect in the rate limiting step of the open formation, which is about a factor of 2. So with this in place, we went ahead and addressed the open formation nucleophilic attack of this oxyl radical, as we had originally suggested. And also we compared the oxo coupling that it was favored in this recent paper by and before by Per Sigmund and coworkers. The nucleophilic attack was ruled out by Sigmund simply because the barrier that he obtains for the nucleophilic attack were as high as 29.8 kcal per mole, while the barrier for a bond formation with the oxyl-oxo coupling mechanism of this oxyl attacking that oxo is 6.2 kcal per mole, as reported in that paper. In our hands, with this extended model of a QM layer, what we find is that the phase is more likely ascribed to deprotonation of OH ligand manganese to the oxyl radical on the dangling manganese that is susceptible to nucleophilic attack by a water nucleophile. And that nucleophilic attack of water onto the oxyl radical was analyzed with free energy calculations. And what we obtained is that the free energy of activation of the O bond formation is 13.2 kcal per mole, very much consistent with the millisecond time scale as estimated by transition state theory. And since we compute that barrier and the effect of isotopic substitution on the barrier, could get kinetic isotope effect for that particular mechanism, and we obtain a value of 25 per thousand, very much in agreement with the experimental data from Gary Bradwick and co-workers. So both the dynamics of bond formation as revealed by X-ray fluorescence and the kinetic isotope effects to be consistent with this nucleophilic attack. And also we observe deuterium isotope effect that it is computed to be about 2 in this bond formation, because the water gets deprotonated, forms a Zund ion with its additional 2 water molecules when the bond forms and the hydroperoxide intermediate is established. At the same time, we took the model reported by Per Sigmund that is much smaller than ours. It's only 104 atoms. And when it's overlaid on the X-ray structure, it exhibits significant displacement of several of the side chains, as well as rotamers that are not consistent with X-ray crystallography. And is missing important parts, such as the presence of valine 185, and has an additional water molecule that would clash with that side chain of valine 185. But nevertheless, with the same model and that model, reduced model, we could address the barrier as well as the kinetic effect. And what we find is, first of all, that the free energy of activation is very much similar to Sigmund report, 7.7 kcal per mole. That is orders of magnitude faster than the millisecond time scale. The kinetic isotope effect is 40 per thousand, so it's significantly higher than reported by Bradwick and coworkers. So this is 22 per thousand, 40 per thousand is up here. So it's way beyond the experimental error of the kinetic isotope effect. And the deuterium isotope effect is about 1, so or slightly inverted deuterium isotope effect. So also this one is significantly different from the experimental data. So from the two mechanisms, we still favor the water nucleophilic attack because it seems to have the correct, the kinetic isotope effect most consistent with experimental data, and as well as the deuterium isotope effect, and the rate that is consistent with transition state theory. How am I doing with time, Jim? I see you're standing up.
Well, I think if you could wrap it up now, because we've
Okay.
got a time problem here, because we've got
Okay.
something going on this evening, and we're running out of time.
Okay.
Thank you very much for making all the effort to get to us. We do have, of course, Holger Dow here. We do have Gary here. So we've got many of the people here, of course, that you've been referring
Fantastic.
to, and they're going to tell us a little bit more about their work as well, of course. So, Victor, thank you so much, Victor. I'm going to ask if. Oh, we'll have a clap first. Yeah. Victor, do you want to try? Shall we try to take a few questions?
Sure.
Yeah. Good. Okay. I don't. It's marvelous. It's working. Who's got some questions, please, for Victor Batista? That's very unexpected.
When you say that the mechanism I have is 7 kcal, the barrier, did you read the diagram I put in? I mean, it's 13. Is it still there?
Maybe Jim can repeat the question.
Yeah, I mean, the barrier I have is 13, not 6. And did you read the diagram? I mean, you have to calculate with respect to the S3 state. And so it's millisecond in my mechanism. So a follow-up is just, what is the energy difference between your S3 and S4 state?
Did you hear that? Could you hear the question?
No, maybe Jim can repeat.
Can you make it a bit louder? Could you shout a bit louder? It's a long way to America.
Should I repeat? Or
You don't have a microphone. Oh, you can't. It's impossible.
yeah, I'm basically wondering, you have, do you hear me now?
Yeah, perfectly well now.
Okay. You say that the barrier I have is 7 kcal. How did
Yeah.
you get that? I mean, barrier is 13 in my mechanism. It is, I have a 7 kcal from S4, but there is another 7 kcal to get to S4. And do you have, when you, what is your energy difference between S3 and S4?
Yeah, so two aspects. Here, there is one step that involves deprotonation of the OH ligand of manganese 1.
And to make the oxygen radical as well.
Yes.
How much does
So
it cost?
that step has a very high energy barrier. So what happens is that OH ligand in our hands doesn't get deprotonated simply because the proton doesn't have a pathway away from the OH of manganese 1. In your calculations, you are able to deprotonate that OH ligand simply because you didn't include valine 185 and you included an additional water ligand bridging between that OH and the
You have to
OH
rotate the
ligand.
valine to get the water there. That's all. And
Was
then
that-
you do that, then there is no interaction. No problem.
Right.
I mean, you must have an energy difference between S3 and S4. What is it?
Right.
What is
So it's 13 kcal per mole. So this is it.
I don't see. I mean, you gave the barrier of 13, but is this with respect to the S3 state or with respect to the S4 state? Because the barrier you gave for me is with respect to the S4 state, where you have to add the S3 to S4 energy.
So once you form the auxiliary radical, if you engage into a all bond formation, you get this energy barrier.
Yeah, but you have to form the radical, which costs 7 kcal at least. So you go up 7 and then you go another 6 in my mechanism, which gives a millisecond rate. I'm also wondering about your, since this is very trivial in a way, I wonder how did you do the isotope effects? Did you compare to S3 or to S4?
So in both cases, we have an intermediate that is formed first,
which
has
goes up.
Equilibrium isotope effect. And then from that intermediate, you go through this barrier that for the non-oxygen 18, for oxygen 16, is 13 kcal.
The trivial comment is that the intermediate is up in energy also experimentally. So you have to add that energy.
Yeah, so we included the equilibrium isotope effect. It's the product of the two. So first is an equilibrium isotope effect that favors binding of water 18, and then a kinetic isotope effect that multiplies that equilibrium isotope effect that favors the activity.
I don't think you answer my question. Is it S3 you're comparing your isotope effect, or is it S4?
So it's relative to S3. After forming S3, what you have is an equilibrium isotope effect that you need to multiply with a kinetic isotope effect due to the all bond formation.
But when you calculate the barrier, you did not use S3. You used
yes,
S4.
It's included in the equilibrium isotope effect.
No, but in the energetics. So you did differently when you did the isotope effect.
Yeah, so again, with oxygen 16 or oxygen 18, you do the same thing. First, you compute an equilibrium isotope effect that equilibrates the S3 state. S3. And then you have a kinetic isotope effect that you have to multiply by that. Yes. That corresponds to the all bond formation. The overall product is what is measured experimentally.
But you have to do the same with the barrier.
Exactly. So the barrier gives you the kinetic isotope.
Well, I think I got enough answers.
I think there's enough for the moment. We have to move on, otherwise we're going to miss our banquet tonight. Anybody want to miss the banquet tonight? Okay, we'll stop there and move on to our next speaker, who's been
too bad I will miss the banquet.
So forgot about you up there. You were just a little tiny picture up the top there, and you look, and it's got underneath it. It says Dr. K. Yang, but I know you're not Dr. Yang. So Victor, thank you so much. We miss you here.
You're welcome.
As I said in my emails to you, we would love to have you here for the discussion. But after what I've just heard now, maybe it's a good idea that you stop over there for a while. Okay then, Victor, thank you very much.
Great seeing you all.
What time is it in the US now?
Here is 4 a.m.
Pardon? It's what? 4 a.m.? You're joking. Oh, wow.